Welcome to my talk on our study regarding the perceptual sensitivity of topological visualizations to feature variations. Now, topological data analysis has shown great promise in visualization to help us understand intricate scientific data sets. And topological visualizations explicitly portray important data features such as local minima, maxima, signal strength, whereas classical color maps implicitly portray these data features. Now, the task of comparing scalar fields is often achieved through their color mapped version or by comparing their topological visualization, as it has been evidenced in multiple real world examples, including climate and biomedical sciences. However, here is the provocation. Although it is clear what features are communicated by different topological visualizations, it is not clear how good humans are at perceiving features portrayed by these visualizations. For example, can you tell where and how much the following two color mapped visualizations are different? Perhaps not. Perhaps they look almost identical and it is difficult to notice any significant differences. And how about these reef graph visualizations which convey topological skeleton of a scalar field? Perhaps it's easier to notice significant differences in the regions marked by dotted boxes. Thus, we investigate what features users perceive when comparing visualizations. We believe that studying such perceptual sensitivity of visualizations is crucial to gaining insight into limitations of existing visualization types, which can provide cues into enhancing visualization design and systems to provide better insights into the data. And the findings of our study will also help guide users in choosing optimal visualization type for depending on the application at the hand. Now, several aspects relevant to our study has been previously studied, and which include factors contributing to effective visualization, perception, then various metrics for quantitative comparison of topological visualizations, and some foundational work in sensitivity analysis of functions and data visualizations. However, to our understanding, no prior work has evaluated feature perception sensitivity for topological visualizations. Now, I'll briefly go through data and techniques that we evaluated and our hypothesis. For our study, our current study is limited to scalar fields sampled on 2D manifold triangular meshes embedded in 3D. We model scalar field as a mixture of Gaussians, which is a common data model used in multiple prior studies. Specifically, we study how much visualization is affected as we introduce variation in amplitude and mean of a Gaussian. Now, I will briefly describe the three types of topological visualizations that we study in addition to color maps, but for more technical details, please refer to our paper. Now, isocontours visualize points with equal data value, also known as isovalues. As depicted for the rabbit dataset, we can control the number of isocontours. Also, we can infer the different events such as birth and merging of connected components, as well as the high spatial density of isocontours is observed in high gradient regions and vice versa. Now, reef graphs visualize topological skeleton of a scalar field, which is depicted with topological arcs and critical points. Specifically, it depicts evolution of isocontours as we increase the function value, which includes various events such as appearance, splitting, merging, and disappearance of isocontours. Finally, persistence diagrams visualize a scatter plot-like visualization where they show where the high persistence features are represented as dots that are farther away from the diagonal, and low persistence features are situated close to the diagonal, which also represent noise in the data. And the vertical distance of a point from the diagonal represents persistence or significance. Now, we use this 1D torus synthetic example for formulation of our hypothesis. The baseline visualizes the Gaussian on a single torus using 4 different visualization types. Now, we observe that color maps are sensitive to both positional and amplitude variation of underlying Gaussian, whereas isocontours and reef graphs show more sensitivity to positional variation and no much sensitivity to amplitude variation, as we can observe based on that the visualization has not changed much for amplitude variation, and persistence diagrams are more sensitive to amplitude variation compared to the positional variation. Now, this was our hypothesis. Now I'll briefly describe our approach for sensitivity analysis of visualizations. Now, here is a 1D example scenario where variations A0 and A1 are about at the same distance from the baseline Gaussian, which is represented as B. Uh, for such scenario, the value of this distance measure A dash is close to 0. Now, it is difficult to tell which variation A0 or A1 is closer to the baseline B. However, as we increase the distance parameter A dash value, it becomes easier to tell which variation is closer to the baseline B. For example, here perhaps it is easier to tell that where the 1D plot for variation A1 is closer to the baseline B compared to variation A0. We apply same concept in 3D. So in 3D, we present a user with 3 visualizations with baseline B in the center and variations A0 and A1 on left and right hands. Users can change the level of detail as described more in the paper, and they can also rotate view and zoom in or zoom out. Users need to visually select which variation A0 or A1 is closer to the baseline B, and if they are not sure, they can also select unsure option in the panel C. Now, here is our approach for measuring sensitivity. Each single experimental trial has its associated measure A dash, which is hidden from users but known to the designers of the experiment, which is us. Now, for small A dash values, we expect users to make a random guess and have accuracy close to 50%, whereas for large A dash value, we expect users to be more deterministic and accurate. Finally, we estimate the sensitivity by estimating the rate of change in selection accuracy as with increase in the A dash value as depicted in the bar chart. We use regression to do such estimation. Now, our experiment consisted of 102 non-expert visualization participants, each presented with 24 experimental trials, totaling to 2,448 trials. And for each user, we presented a tutorial and practice session to get familiar with visualization types and features to look for, as illustrated for persistence diagram on the right hand. We conducted a between subject experiment with parameter distribution with following parameter distribution, where we assign 6 trials per visualization type, then 12 trials per variation type, and so on. Finally, we conducted study on Amazon Mechanical Turk for users with hit approval rate greater than 95% for higher reliability of results. Now, first I'll present the accuracy result. We calculate accuracy as number of correct selections divided by number of total trials for a given visualization type. And our hypothesis is that for small A dash values, we expect accuracy close to 50%, whereas for large A dash values, we expect higher accuracy. Now, our hypothesis was statistically significant for all visualization types except for the REEP graphs, which had high p-value. Now, REEP graphs stood out and caused us to reject the hypothesis. They had overall lower accuracy due to their discrete and high frequency nature. Also, most users voted REEP graphs as the toughest visualization type, whereas color maps as the easiest visualization type. However, more than accuracy, we are concerned or more interested in the sensitivity of each visualization type. Now, for color map visualization, we our observation validated our hypothesis that it is sensitive to the amplitude variation, whereas our hypothesis regarding positional variation was rejected, where we can see that color maps are not sensitive to position, as we can observe through the flat line as well as through the high p-value. Now, isocontours were in the least agreement with our expectation. We hypothesized that isocontours will show high sensitivity to positional variation, but they did not, as can be seen through flat line. And also we did not expect them to be sensitive to amplitude, where they showed some weak sensitivity to amplitude variation. Now, reef graphs and persistence diagram both validate observations for both validated our hypothesis. Now, this can be considered as a asset as well as liability. Asset is that our hypothesis is validated, whereas the liability is that um, each of the visualization types only conveys one type of variation. For example, persistence diagram only convey amplitude variation but no positional variation. So that's their shortcoming. Now, uh, yeah, so to summarize, uh, both reef graphs and persistence diagrams validated our hypothesis, whereas the hypothesis was rejected for most cases in color maps and isocontours. Thus, the main finding of our study is that there is no single visualization to rule them all, or in other words, no single visualization type can convey both position and amplitude variation effectively. This necessitates to investigate the need for multi-view visualizations to combine more than one visualization types and enhancing existing visualization design for better portrayal of features and enhanced sensitivity. Now, there are several limitations of our work, and I won't go into each limitation, but essentially, few important ones are currently our participant pool comprises non-expert visualization people, and but we need to cover more diverse pool of participants. However, we ensured that the tasks were relatively simple and did not require visualization expertise to conduct our study. Um, we consider our data currently we have modeled it as a mixture of isotropic Gaussian functions that are embedded that are for 2D manifolds embedded in 3D. However, we want to cover more complex functions and 3D volumetric data sets in the future. Also, we have evaluated 4 different types of visualization, but other visualization variations such as planar reef graphs, Morse complexes, multi-view visualizations still remain to be investigated. Thanks for your attention.